this is session 4, the last one for me. At least there's one more after from some folks at Moodle AI who will show you maybe something a little more practical about it than the things I'm showing you here. So in this session, now that we've built some intuitions about model learning, we've learned how what deep generative models look like, how to learn them. We're gonna look at how we can use not just our this sort of abstract knowledge, but really build in a very concrete way on the model and the inference procedure that we used in the VAE example. And so to that end, we're going to look at 2 case studies. First is in extending the VAE model by adding a single new latent variable and troubleshooting SVI in the extended model, because things never quite work out of the box. In the second case study, we'll look at a different extension of the VAE model by tiling it sequentially and building up a new guide and inference procedure with a sequential dependent structure that corresponds to the model for sequential data that we built. These 2 case studies are based on following Pyro tutorials, or these 2 Pyro tutorials respectively. The semi-supervised VAE, which is called that for reasons that will become clear, but we shouldn't dwell on the name too much right now, and the deep markup model. Both of these are on Pyro's website, our examples webpage. Okay, so in the last tutorial, we looked at decoder networks, or this decoder network, which is sort of the simplest deep generative model that we could come up with. We take a bunch of independent noise, feed it through a neural network that parameterizes some final distribution that we finally sample some data from. And as you can imagine, this approach has limits. It quickly runs into difficulty in learning models that are useful on data that's not quite as trivial as in this, precisely because it has so little structure. And so we're going to look at, as I said, we're going to look at adding in a little bit of that structure back to the model, a little bit of knowledge that move things slightly beyond this total black box decoder network that is that's widely studied in sort of more researchy machine learning right now. Okay, so let's just briefly revisit the results from the last example, the VAE example. Just to recall the model briefly, right? There's a neural network decoder. We sample an independent latent code and feed that through a neural network, and finally sample a data distribution. In this case, a Boolean distribution over the pixels. And remember what that produced. So we fed in this data, learned this model, which is here described by its graphical model. And we visualize these results. We visualize the latent codes, the posterior distribution, or the means of the posterior distribution of Z for each data point X. We embedded those in a low-dimensional space, colored them by their class, and visualize them. And what we see is that most of the variability, it seems, in this latent code Z, is going towards explaining class variability. But we might not want that, right? Or we might want our model to explicitly account for that source of variability, which we'll call class, as opposed to variation, say, call style. So we'd like to slightly extend the VAE, this completely black box VAE decoder network model, so that it separately explains class and style. And the way that we're going to do that is we're going to explicitly add a second latent variable y, in addition to our latent code z that we had before. And y should only explain class, or to the best of our ability, should account for all of the variability between clusters that you see here. So ideally, this picture, the colors would be all muddled up. You wouldn't necessarily see all the reds off in this corner and none over here. It should all be muddled up if we were to just visualize the z's. If we could get this model to work. So what does the model look like? Well, it's pretty simple, right? We just add a single line of code. We add another sample statement with a categorical distribution, which is a distribution over these discrete index variables, like 0 through 9. And now our decoder will take, in addition to taking the style variable z, we'll also take this variable y as input. So the decoder now has two arguments, z and y. Okay, well, so remember, our model, our decoder is still a complete black box, and there's not really any particular reason a priori that the model should actually use right now, should use class, should use y to parameterize the variability between class in particular. There's nothing, although we like this variable y to account for class, we haven't yet done anything to the model that would actually force it to learn that y is class, precisely because our decoder network is still just this black box, just like the one that we would use in the one we used in the VAE example. It's just an altogether perceptron. So we'll make a second departure in the model. To encourage this variable y to explain class and only class, what we're going to do is, for a few images, although not for all of them, we're going to observe labels. We're going to collect some labels. And now, when those are available, we'll feed them into the model so that they're observed. See here, our sample statement y now has an observation of the label value if y is not none. And if y is none, obs is none by default, so it will be as if there was no observation. So this means that, in principle, if we could compute the marginal likelihood exactly, this log evidence exactly, then this should provide strong pressure on the decoder to use y as a variable, as the feature that explains this between class variability. So remember, the name of this tutorial on the Pyro website was the SS, Semi-supervised VAE. And the reason we call it semi-supervised is because we're using a few labels here to help learning the model, to help the model behave in the way that we would like to. Okay. So we have a model in hand, which we should be reasonably happy with. How should we now, since we still can't compute the marginal likelihood exactly, as always, we have to resort to approximate inference. Sorry. How should we extend the guide from our VAE example? So we have this guide that we built that was sort of small conceptual leap, which seemed pretty useful. How can we extend this to also handle this y variable. In particular, we'll need to solve the same problem of we'll need to find a way to encourage the guide to exploit or via the class labels to exploit y as class information. So let's imagine for a moment that we were always given a class label y. We can then use that as a covariate to predict style, to predict z for a given image. Right? If I was just given y as an input, as I am here, all the time, then I could just take my encoder network, right, this thing that takes in the data, and additionally pass in y. And at that point, you know, the guide shouldn't need to do, given enough data, the encoder should learn to separate class from style on its own. Z shouldn't need to do any additional work explaining class, because y is already doing it. But obviously, so remember that we said that we're only collecting a subset of labels for these images. So what about the case when no labels provided? So we'll do kind of the simplest thing we can think of, which is that we'll have the guide when there's no label. We'll have it guess the label. There will be another VAE style guide, right? Another neural network that parameterizes another latent variable. In this case, categorical, because y is categorical. It's discrete. And we'll just use this encoder to guess what the label would be if we weren't given one. And then we'll pass that to our style encoder as we did before. Okay, well, it seems like we're in a pretty good place right now. It should mostly work, right? We built in a minimal amount of bias, and if we provide some data, then we should get a pretty good model. We should get the effect that we want. So if we do inference in the usual way, right? We just take our VAE sort of SVI loop code. Create our SVI object just exactly as we did before, the same elbow, same update step code, except that we did sometimes pass in labels y. Unfortunately, what we see here, if we treat that encoder network as a classifier, since it's predicting the parameters of a categorical distribution, we can treat it as a classifier. We can measure it as a classifier. We extract it and measure the top one accuracy through training on a validation test set. What we can see here, I guess the numbers are a little small, but what you can see is that it's kind of oscillating wildly, and it never really gets above chance. It never really gets above 10 or 15%. Remember, there are 10 classes because they are digits 0 through 9. So, back to the drawing board. Why are the classification results so awful and volatile? Well, one possibility is that the gradients that the encoder, the classifier, is getting for its weights are way too noisy for it to follow in any useful way. Remember the updates. Remember that when I showed you in the VAE example, the implementation of a simplified elbow, a simplified Monte Carlo elbow. Remember that we're approximating the elbow by Monte Carlo, which means that there is noise in our gradient estimates because we're taking gradients of this stochastic, this noisy function. And it could be, in fact, it turns out to be the case that the gradients in the source of all this noise is that the gradients for parameters through a categorical variable are extremely noisy, extremely high variance. So, what to do? So this is one of the advanced features of Pyro. One of the things that we put some of the most engineering effort into.
Can I ask? Usually in deep learning, whenever they have discrete values, the recipe is embedding. Is it something we're going to do here, or just map it to a continuous space? That you
no, I mean, we'd like so an embedding is kind of like a, I don't know, I suppose it would be like a different model, right, for the, and we'd like to keep our model the same. Like we'd like to explicitly have a class variable. This is a very nice little generated story. And so we can, we'll try troubleshooting inference here rather than modifying the model. But this problem of gradients flowing through a discrete variable is generally, it's sort of for the very simplest kinds of variational, the very simplest forms of the kind of variational inference that Pyro implements is a bit of a showstopper. And so you have to, there's a lot of work that goes into different ways of dealing with this, of reducing the variance, the noisiness of the gradients of things that are hidden behind discrete variables. So in this case, what we'll do is, rather than having our classifier, rather than in our guide, having it guess a single value, a single class, we'll have it guess all possible classes in parallel. And all we have to do that, so this is as an aside, is one of the features that we put in the most engineering effort in Pyro is the general problem of dealing with discrete variables in SVI, and especially the solution of when possible enumerating them in parallel. So all you have to do is use this function, this decorator higher order function, which is also implemented again with the same. It has a very simple implementation internally, the same routine logic that we saw at the end of the last tutorial. Same is implemented with some of the same building blocks. And what it does here is it just marks all of the discrete sample sites, things that can be enumerated, and tells the inference algorithm that it should try expanding them and enumerating them in parallel instead of sampling. And so the thing that actually handles that is this different elbow implementation. So we've been using pyro.infer.traceElbow this whole time. We've used that for every example so far. But here we're going to have to, because of this problem of variability, we're going to have to depart and use pyro.infer.traceEnumelbow. And these approximate the same objective, but traceEnumelbow is smart enough to be able to take advantage of these enumeration annotations when possible. And so we just pass traceEnumelbow into our SVI object instead of traceElbow, and we'll have another go. So we decorate our guide. We create this slightly modified SVI object, which uses a different loss, or a different implementation of the same loss. And we run the inference loop again.
So so how does this scale when you have say n labels, right, and all discrete?
It scales within.
Pardon me?
It scales within. There's no asymptotically, it doesn't scale favorably, right? There's no trick to enumeration. It literally just tries things in parallel. It uses broadcasting to vectorize the evaluation in parallel. And then you can also take advantage of independent structure.
So could you change your model to assume that the y is always present, but there is another thing that comes and ablates it? Like for example, there is a missing variable, like an m variable that comes and destroys your y for certain examples.
So would that be like the scenario where the the scenario that we're in now, except that we have labels for most of the
Yeah,
Ys
it's
instead of a few.
exactly the same model, same data set, right? But what I'm saying is there any way to like salvage the previous version of the guide where you didn't have parallel enumeration, right?
Well, the guide is actually, the guide code is actually completely the same. The only difference is that we've added this extra annotation. The internals of the guide haven't changed.
Including the if it's none, then do.
Exactly, yeah.
Okay.
Yeah, that hasn't changed at all. We've only added this behavior on top. Yeah. So I think like it's a bit of, you know, it's obviously like from a, it's pretty clear, right, that there are scalability issues with enumeration. So, you know, it is on some level brute force. But we find, I think that, especially when paired with other strategies for reducing variance, actually, like we don't, in general, like having a, probably if you have a model with an enormous categorical variable, right, and a very large m, or in, right, it could take many values, you know, it might have 1,000 class labels or 1,000,000 class labels instead of one. Then honestly, probably that's not a very good model. Not a very good model. It doesn't concisely encode a description of your data.
No, but you can imagine that you have some word classification.
Oh no, these things totally pop up in practice.
Yeah.
And if you have a you know, and obviously you can't use enumeration for the really big ones. But so in this case where we use you know, where the Y is part of our generative story, it's part of our belief about how the data got generated as opposed to maybe like some sort of fixed part of a particular problem. Then if it was too large, then the inference benefits of enumeration are such that we might actually seek to, you know, modify the model to maybe better encode some assumptions. As a kind of aside, I guess there's this bit of this notion of a folk theorem of statistics, which is that if your inference algorithm isn't giving you the results you want, then the problem is probably with the model. And I think that's actually kind of, an extremely useful intuition when you're working with probabilistic programs. So there are definitely problems where you know, especially in things like language, where you can't avoid large discrete variables. But in other cases, you actually might be able to get away with modifying your model. And that's part of the strength of probabilistic programming is that you're allowed to do that. And it's really not to, you know, pay a big overhead. Yeah. And so to return to the effect of enumeration, of replacing our guessing a single label with enumerating all possible labels in parallel, weighted by how likely the guide thinks they are. What we see is that now these numbers are still pretty small, too small, but now we can see that the classifiers are eventually getting up to around 90% accuracy, which is certainly better than chance, certainly better than our 10-15% that we were seeing before. But it's also, if any of you have ever even played around with you know, classification or inits or something, is pretty awful.
So can I ask again? You're saying that it does the inference in parallel. Does it mean that I don't get that the guide is generating a sample, you know, Z and a class. Like, do we require for the guide to do that multiple times, or?
I haven't gone into this in any detail because unfortunately it was too much to fit in. But one of the central tools in Pyro in practice is this idea of broadcasting. So for those of you who are, most of you probably are familiar with NumPy, and you're familiar with this idea of broadcasting, where, for example, you try to add a scalar or a vector in a matrix, then the smaller thing will be will have a dimension added on the left. use the same idea, so that you can add those things together. And in Pyro, we use the same idea pervasively. So to implement enumeration, actually, you might imagine having a single sample, except that now it's been expanded along a new dimension, so that each of those dimensions has one value from the possible enumerated values, and that could be because all of PyTorch has the same broadcasting semantics. All those operations can be broadcasted and run in parallel.
So in your guide, had you used a one-hot encoding for your y rather than a categorical like 0 to 9? Could you have used? Could that have improved your gradient estimate?
No. The problem is more it's an abstract problem with taking a gradient through a discrete variable. So the one-hot categorical still takes on a finite number of values. So there are different kinds of approximations you could do, but under the different implementations, the same problem, and really because it's the same model. The same
I mean, for the cases where you're predicting, right? You don't have to take the max, for example.
Yeah. So that's definitely possible, right? That certainly happens in practice, especially in language-related problems. But it is a different model.
I mean, conceptually, I get it that if we had a discriminated model, we get a softmax, like it would predict. But I can't get it the inverse of that. Like I understand that you wouldn't say it would be a probability over 10 different classes. But how does it? I mean, that's what I don't get over here, because now it's a generative model, so it picks one. I don't know what
because of the broadcasting semantics, it picks. The rest of the model can think that there's only one, but there's actually this extra dimension way out on the left, which has values for each one. And so all the operations will be broadcast along that dimension. There's a Pyro tutorial on that, Pyro tensor shapes in Pyro 1.2, which is also on the webpage, the examples webpage, which is, if you're interested in more details about this, I would highly recommend that folks look at. Again, it's like, for the Pyro team at least, this is near and dear to our hearts, because this is where a lot of our effort's gone, our engineering effort. Okay, so as I said, the classifier accuracy is much improved, but it's still pretty low. Right? It's still really inexcusably low for a NIST. One possible explanation for that is that if we return to the definition of the guide, we'll actually see that our encoder, our classifier, is never actually trained on the ground truth labels. So if y is none, this whole thing is just skipped. The encoder is never evaluated. And so what we'll do is we'll build an auxiliary model. We'll actually explicitly train, in addition to having the classifier live within the guide, we'll build another model that only contains our classifier, our encoder. And we can also, and we'll explicitly train that on our labels when we have them. And because there are no latent variables in this model, right? So we're only ever going to call this model when y is not none, or we're only ever going to do inference when y is not none. So there are no other latent variables here. There's no randomness. It's just a classifier. It's a standard deterministic classifier. Then we can still train this. Syntactically, we can still train it with SVI. We can just use a guide that has nothing in it. It's trivial because there are no latent variables that pass the model.
That's not a probabilistic model.
It's a probabilistic classifier. It's not a latent variable model.
Which are the probabilistic variables here?
Well, y is the loss that you're training. You're still maximizing the likelihood of observing a label when you pass on y. But it's no longer variational. There's no inference because it's not. There are no latent variables. So it is a little strange. It's a little strange to think about. Okay, and in terms we modify our inference code in this way. So we've got this slightly modified SVI that we created before, which enumerates in the guide, and also, I guess I moved it for space, but also uses this trace enum elbow. And then we also have this auxiliary classifier training step that we built in the last slide. If we do this, then now we're getting accuracies that are kind of in a respectable range for the relatively simple neural networks that we're working with. We're getting above 96%, which is still not great. But remember that we're only working with maybe a few hundred or 1,000 actual class labels here, so it's not the full data set. Or it's not the full label data set. So it's pretty cool that even though we didn't have labels for the full data set, we still have a classifier that's with calibrated uncertainty that's doing a pretty good job of guessing the class of the digit. And the punchline is, so remember, I showed you we saw the cloud of embeddings from the VAE example, and they were clustered into according to class. And if we do exactly the same thing here, if we visualize the same thing, a low-dimensional embedding, TC embedding, say, of the digit style vectors, the z vectors, then now, as I said, or as I said we would hope for, now all the colors are spread everywhere, and the y variable is currently doing all the explaining of class, and z is allowed to sort of vary conditionally on that. And here, if we actually clamp y to be a particular value, in this case 0, and we sample forward from the model, we see that it's actually learned to generate good images. These all look like zeros, right? They seem to be sharper, more well defined than the ones that we had before. And then there's some quantitative results here, which show basically that which are effectively the final numbers from the accuracy plots that I showed you. So yeah, that's case study number 1 of how to extend the VAE to work with to have an extra latent variable that will explain this bit of variability that we saw when we were analyzing our model learned. So the next case study that I'll kind of breeze through a little more quickly is the problem of learning a deep generative model of, in this case, of MIDI music, actually from Bach, digitized Bach. It's actually Bach. Fun-looking guy. So Bach's here is humming to himself X1, X2, X3, and presumably he has some latent variables in his head, right? Like say music notes that explain the sounds that are coming out of his mouth. And in statistics, right, and other fields, right, this kind of model where there's a sequence of latent variables that generate conditionally independent observations is called a state space model. And we're going to build a deep version of that, which we're going to call a deep markup model. We're going to replace each of these little transitions with a black box neural network, just as we have in the VAE. So let's again consider the decoder network model from the VAE example. This super simple black box deep generative model. How could we extend this now for sequential data? When our data isn't completely independent, but we have independent sequences of data, sequences of musical notes from different songs, or sequences of MIDI indicators from different songs. So that this dependency graph of a state space model suggests that we should compute instead of hard coding these parameters of z of our latent code z to be 0 and 1. We should instead compute those parameters from previous values of z in the sequence. So we could pass some parameters as arguments to that VAE model, the decoder network. Instead of having a 0 and 1 here, and then proceed as before, this time with a normal distribution as a likelihood for our observations. And then we could just put this VAE model, right, this slightly modified decoder network into a for loop. And so now we're going to sample an initial Z, which is independent, and then in this loop over a single sequence, we have this neural network transition, which takes in the previous value of Z, our latent code, and computes parameters for the next value. And those are fed into this VAE model that we modified from the standard one.
Just for the clarification, the parameters of the decoder, are they also random variables?
None of the neural networks are parameterized. The neural networks all have deterministic parameters. So that's right. Sorry, I've been a little loose with my terminology of the things I call decoder. Yeah. Okay. And transition is just another MLP, kind of like the ones that we've been seeing before. So multi-layer perceptron, just a bidirectional network. One other brief note is that you can see here that we're passing. We'll need to pass this. Remember at the very beginning, in the first tutorial, when we were talking about building up models from simple models, that we need to make sure that names are unique. So in this case, we'll pass in the loop index t, so that we can compute a unique name from t for each new late variable and each musical note and each actual sound. All right. So what about the guide then? How should we extend our simple VAE guide to capture dependence across time? It does seem kind of silly now to consider having those. We could do the usual thing that we've done, right, and just make everything completely independent. But that seems kind of silly. It's clearly not going to work. So one thought, analogous to the model, is that we could provide the VAE guide for each step, each late code Z at a particular time step, with the late code Z from the previous time step, just as we do in the model, as well as providing the data at data point X. And then just briefly recalling the structure of the model, we could create another for loop where for t in some sequence that isn't quite this one, we'll call the VAE guide in some sort of loop. But the details of what's going on here are critical. That's what determines whether our guide is a good one or not. And it's a little bit more subtle. You might think. So this is from a paper that this model was originally specified in. It turns out that if you were to actually do a little bit of, if you were to apply those rules of probability, in fact, in particular Bayes' theorem, to compute the dependency structure, let's say, if we wrote down the joint distribution of the joint probability distribution of the model, all the variables in the model, and then we tried to compute, we applied Bayes' rule to compute the probability distribution of a particular latent code given all the observations, a particular Z at time t given all of the observations, all of the musical notes, the musical sounds in the song in the sequence from beginning to end. What we actually find is that dependent on all of the observations throughout time. The true posterior depends only on the latent variable from the previous time and all of the observations from the future, which kind of makes sense, right? All of the information about the past by design is captured by the latest variable, the last latent code. That's the design of a state space model, or a hidden markup model, or any other similar thing. So instead of doing something that's exactly the same as the model, what we can do is instead of to our VAE guide giving the data point, the observation, at a particular time, we could pass in a constant size feature that summarizes all future observations. Remember, the value, the distribution of Z2 here depends on Z1 and on all values of X from X2 to however long the sequence is. So we could reduce those down to approximately in our guide. We can encode that dependency structure by computing a constant size feature of that entire sequence of future observations, which we'll call H. I've written this H here in correspondence with the picture. And then, as we've been doing, rather than thinking really hard and trying to come up with the right features, we'll just attempt to learn them with a recurrent neural network. So those H's will be the output of a recurrent neural network. And now, instead of a data point X to be passed in to the per time step VAE guide, we'll pass in the features that recurrent neural network computed for that time, which now has information about the entire sequence. And again, you see we pass in the time step T to compute a unique name for the Z, the latent code. So there are models compose. Yeah, and the upshot is that there's more in the tutorial about making inference work in this model that I don't quite have time to go into. But the upshot is that once you do a little bit of extra modification, things work pretty nicely. And this is a graph that shows an estimate of that log evidence for the model for a particular data set of Bach music, a toy data set of digitized Bach music, and it shows that this number that it converges to down here is ends up being exactly the same or slightly better than the number that was reported in the original paper, where they implemented everything by hand and did all this optimization and inference and that sort of thing. So I think this is a kind of a testament to the ability of now maturing probabilistic programming systems like Pyro to really work. You take a model that's not completely standard, that doesn't fit on your scikit flowchart, and do a little bit of extra work and to make inference work. Follow what I think was a fairly logical troubleshooting process of checking the assumptions that we made and building the model guide. And at the end of the day, you get models that really work, behave the way you want them to, and learn in a reasonable amount of time. Yeah, so that's pretty much it. I think about time.
I think we have 6 minutes over time.
Oh shoot! I'm sorry.
That's fine. So, are there any questions before we go to the last presentation? I have a philosophical one, which is what you described in the last session is something that people also call the infogram. And I mean, it's kind of like the elephant in the room right now, okay? So we haven't mentioned GANs at all. What's kind of like your take, like, do we get better performance with GANs? There's like 1 million different GANs doing different stuff. Why should we use this type of generative models and not go to GANs? Like, what's what's your take on that? Why did you take this approach and not the GAN approach?
Well, I would say first that I think they're orthogonal, right? So in our VAE example, remember we parameterized the actual pixel distribution as a bunch of Bernoulli distributions parameterized by some probability. And again, you wouldn't have an extra distribution there. You have a neural network that takes in the latent code and spits out an image. And then because that doesn't have a tractable probability density, tractable likelihood, then you have to use GAN techniques, discriminator, to train them. And so you could write exactly the same sort of algorithm in Pyro. You can use it as a component. So I guess the deeper philosophical point really is about the value of latent variables. Like, why should I, let's see if why should I do this instead of this? Which is what, which are the models that appear in GAN papers. And I guess there are a bunch of reasons. One is interpretability and troubleshooting, the ability to do things like causal inference. Yeah, but so my answer is yeah. So they're orthogonal, and you could certainly implement, and people do implement this sort of thing in Pyro and other PPLs, like Edward, for example, which is another PPL that focus on variational inference in TensorFlow. Has some GAN inference that allows you to use distributions that don't have tractable likelihoods. So I think the big takeaway is to think of everything under this unified umbrella probabilistic modeling. It's a really useful perspective. I hope I persuaded you of that, you the audience.
I was. Okay, so let's thank Eli for doing this 3 hours on his own. Let's move quickly to the last presentation.